Someone is trying to join, I think. No. Is that full house today? You can see my screen?
Yeah.
Yes.
Hmm. Okay. Hmm. So you can see that. So you see, when you learned about sets, the very next thing that you learned was subsets, right? When you learn about sets and subsets, then you learned a relation between two sets. Like if A, B are two sets, then how do we relate to sets? We relate to sets by a function from A to B, right? When we talk about groups, the very next thing will be talk about subset of a group, but not just any subset. Okay, a subgroup. So whenever we will study vector spaces, we will talk about subset of a vector space, but not just any subspace, not just any subset of a vector space, a subspace. And we will talk about maps between vector spaces, maps between topological spaces which are known to be continuous functions, maps between any two sets which are functions. Okay, so whenever we talk about objects, so whenever we talk about, whenever we introduce a new object, I write this object word inside inverted commas. We have to discuss about morphisms between two objects and sub objects. Don't be afraid of these terms, we will explain them. So let's write object here, let's write a draw table. Okay, let's write object here, sub object here, sub object here, sub object, sub object here, and morphism. Okay, so this is a table having 3 columns. My handwriting is horrible. It is a little bit more understandable when I write on the iPad, but in laptop it is just, I mean, horrible. So whenever we are talking about sets, the object is a subset. Okay, and the morphisms are functions. You see, a morphism is basically a particular type of relation between two objects. Like a function is between set to set, right? So whenever we say groups, we have subgroups. I think all of you have the definition of subgroups already known to you. Then there are group homomorphisms. We will talk about this today, don't worry. Whenever we talk about vector spaces, I think some of you know what a vector space is, some of you don't. I mean, don't be worried too much. We will talk about everything. Okay. Now tell me this thing. So what is the definition of a subset? Anyone? Definition of a subset. So let S be a given set. S be a given set. Okay. Tell me what is. So S prime is said to be a subset of S if what? Please complete the sentence. If what?
If S prime is contained in
If
S.
S prime,
Yeah. I mean, both of you. Go ahead one by one. Ladies first.
if every element of S prime is belongs to S.
This is Tamanna, I think, right? This is your voice.
Yes, sir.
Okay. I am not yet familiar with your voice. Okay. I mean, who was next?
Yeah. If S prime is contained in S.
No, you see, I mean, I mean, whatever someone wants to join this call, but who is it? I mean, you see, whatever Rohan, this is the basic group theory class. Okay, you can join it, no problem. But where is Onjil?
ওকে স্যার
না এটা বেসিক গ্রুপ থিওরি ক্লাস করতেই পারিস, কোনো সমস্যা নেই, তাহলে অঞ্জলিটাকে ডেকে আন। ওকে, so you see, I mean, what Tamanna said was that if a subset of S, if for any x belongs to S prime, we have x belongs to S, right? That was your definition, right? And you see the problem, I mean, the one you said, I mean, who was it, by the way? I forgot again. Audric it was?
Shobhoshachi.
No, Shobhoshachi. The problem is that when you say S prime is content in S, what do you mean by the word content?
মানে S prime এর এলিমেন্টস গুলো S এ থাকবে।
Yeah, so basically you are telling this, right?
Yes.
But can we define a subset S prime of S in the following way? That S prime is a subset of S if there exists an injective map which we known to be the inclusion map. Okay, S prime to S denoted by I. What does it do? So I is from S prime to S. What does I do? I sends x to x. Okay, this can be regarded as an alternative definition, right? I mean, one thing is obvious to you guys, I think, that if S prime is a subset of S, then there is an inclusion map, right? X going to X prime, right? X going to X. But I think you guys are thinking that why should be for any injective map? I mean, I can understand that. I mean, you think that there might be injective map from, I mean, various sets to S, right? Not every one of them should be a subset of S, right? That's your, I mean, that is your main confusion, I think.
Yeah.
That if S prime is a subset of S, so I mean, you are okay with this. If S prime is a subset of S, then there exists an injective inclusion map. I mean, you are okay with this. But if I write this if here, I mean, if I write S prime is a subset of S, if there exists an injective map say J from S prime to S, then you are having some problems, right? I mean, S prime may be outside S, right? Okay, so I will tell you one thing. Don't use these definition in your college. This is a strict one, okay? Don't use it. They will probably ask you something which you don't know, okay? I'm not telling you the complete picture, but I'm trying to show you something. Maybe, I mean, see, I mean, this is a, whenever there is an intense course, you may not understand whatever is, I mean, you may not understand why do I need to define it this way. I mean, this definition was perfectly good, right? This definition. Why am I talking about this definition even? I mean, if star is so good, why do I need this one? But soon you will understand why. So you see, what do we do? If S prime is any set from which there is an injective map, this is the notation of an injective map, okay? Then we identify S prime with the subset Js prime of S. Clear now? So we are identifying Js prime, I mean S prime with its image inside S, okay? Soon you will see, I mean, whenever we go to, I mean, a little bit higher, that every time you say a subspace or a subgroup, you will need this injectivity, okay? That's why I am telling you this. Okay, so all of you know what a definition of a subgroup is, right? So H subgroup of G if H is a subset of G and H is a group itself, right? Okay. What about group homomorphisms? So let if G to G prime be 2. Okay, you see, whenever we go to Hungerford, you will see a lot of notions of semi-groups or something like that, okay? You don't need to pay attention to those things. We are not talking about monoids or semi-groups. We are only bothered about groups. Clear enough? We are only bothered about groups. Okay? So let if from G to G prime be 2. No, sorry. I should be writing. Let G prime be 2 groups. And if G to G prime be a function satisfying the following. First, if of G1, G2, or maybe I should write AB, if of A dot B is equal to FA, so you can see that this A dot B, this dot is in G, right? And this operation is in G prime, right? Because A and B, for all A, B belongs to G. So whenever we are multiplying A with B, the multiplication is taking place inside G. And whenever we are multiplying FA with FB, the multiplication is taking in the codomain. Okay. So this is the first criteria. I am writing out two more criteria. Tell me if these are needed at all. F of A inverse is FA whole inverse, and C, F of EG, that is the identity of G, is basically F of EG prime. Tell me, are these two criteria redundant? I mean, are they even needed? Or one will imply these two?
ওয়ান দুটোকেই ইমপ্লাই করবে।
How?
মানে এফ অফ ই কে তো আমরা এফ অফ ই হিসাবে লিখতে পারি, তারপর যেহেতু এফ অফ এ বি ইজ টু এফ এ ইন্টু এফ তে ভেঙে যাবে, তাহলে ওটাকেও এফ ইন্টু এফ তে ভেঙে দিতে পারবো। আর যেহেতু ওই মানে রাইট হ্যান্ড সাইডে যে ইয়েগুলো থাকবে ওগুলো তো জি প্রাইমের আন্ডারে হবে, তো হবে ইয়ে হয়ে যাবে। মানে এমনি এখানে বলতে পারছি না, মানে মুখে জিনিসটা বলতে পারছি না ঠিক করে।
I mean, whose voice is this?
সব্যসাচী।
So you see, I mean, the problem is that, so I mean, if I write, so he is saying take B equals to A inverse. Okay. Now you see, A into A inverse should be equal to FA into FA whole inverse. I mean, FA inverse, right? You know. FA into FA inverse, right? And he is saying that this is nothing but EG, right? Now what? Subhajaji? If you have 1 and 3, you can say 2, right? If you have 1 and 2, you can say 3. But from 1, can you directly say this?
আচ্ছা এফ এ
এটার জন্য তো 3টা লাগবে, মানে যেটা তুমি প্রমাণ করছো ওটার জন্য 3টা লাগবে।
But can we prove 3 directly?
1 দিয়ে করা যাবে 3টা।
না মানে এফ এ একটা এলিমেন্ট হবে জি প্রাইমের, আর এফ এ ইনভার্স হবে সেই এলিমেন্টের ইনভার্স ইন জি প্রাইম, তো ওটা বেসিক্যালি আইডেন্টিটি পাবো না আমরা, মানে জি প্রাইমের আইডেন্টিটিটা।
No. I mean, okay, it's better if we can, I mean, keep the conversation in English because Tamanna doesn't understand Bengali. So, no, you think, I mean, tell me, how can I do this? I mean, okay, then let's prove that 1 implies 3. Okay, let's prove that 1 implies 3. So take A equals to B equals to EG. Okay, so now you have f of EG into EG is equal to FEG FEG into FEG, right? But EG square is EG, right? So FEG is equal to what? FEG whole square. Then what? Now you can multiply this with FEG whole inverse, right? See, FEG, I mean, where this operation is taking place, this is inside G prime, right?
f of e is in G prime, so it will be
Exactly.
equals to the identity or element of G prime.
No. Why are you assuming that? Who told you that? We are trying to prove 1 implies 3.
Oh, okay.
Multiply this by this thing. You have to prove it. I mean, it is not direct. I mean, okay, it follows, but you just told me that you need only 1, you don't need 2 and 3, then you better prove 2 and 3 from 1. So now what do you have? This inverse is happening in G prime, right? Thus you have this. Okay, now 3 is established. Okay, 3 is established. Now you see 1 and 2 will imply 3, so 1 implies 3. So we have 1, if we have 1 then we have 3, then from 1 and 3 we can have 2. That is easy. You can take f of A and A inverse is equal to FA into FA inverse, right? And this is what? EG, and we have already shown that f of EG by 2 is EG prime, right? Hence f of A inverse is f of A whole inverse, right? So 1 is enough. Okay,
আচ্ছা দাদা,
বলো।
3 এর RHS এ তো হয়েছে f of eg প্রাইম, আর আমরা এখানে প্রুফ করলাম শুধু eg প্রাইমটা। 3 এর যে স্টেটমেন্টটা লেখা সেটা f of eg is equal to f of eg প্রাইম করেছি।
No, this is a typo. I mean, identity of the domain should be sent to identity of the codomain. That's it. Okay. Whenever we have defined, so let's go to some examples. Okay. So first example, which is two very obvious example. One example is this.
আচ্ছা, উপরের পেজের লাস্টের দিকটা একটু দেখাবে?
টুকছিস নাকি?
হ্যাঁ,
না, the note will be sent. Take it.
আচ্ছা,
right. The identity map. Okay. You are sending each element to itself. So identity map is a group homomorphism from itself. Okay. Example 2. How should I write it? Is there a notation particular? No. Maybe just write it. The trivial map. That is, it is also from G to, G prime. G prime can be any group. Okay. G prime can be any group. You will send every element from G to EG prime. Okay. And you will see that this also is a group homomorphism. Okay. Example 2. Let H be a subgroup of G. The inclusion map. Now you will understand why I was spending so much time there. The inclusion map, sending H to H. Is it a group homomorphism? Is it a group homomorphism? Anyone? Anyone?
ম্যাপটা কিভাবে কাজ করছে আরেকবার দেখাবে?
Just the inclusion map. H is a subgroup of G. Do you guys know about the inclusion map? So H is a set, G is a subset. I am sending each element of H to itself in G. That's it.
Yeah, homomorphism.
এটা কে বললি রে? Whose voice is this?
Samanya.
Yeah, good. So this is very easy to check. I mean, what the hell are you guys doing here? You take H dot H prime. What will be that? H into H prime because of this map. Isn't it H into H prime in, I mean, the multiplication is happening inside G. I mean, this is vacuously true.
Yes.
Yes.
Okay. This is example 3. Okay. Example 4. I mean, see, from example 3, there are some obvious examples. You know that Z is a group, Q is a group under addition. So you can think about from Z inside Q. Okay. Sending, I mean, M to this. Okay. Right. And also, like, you can think about the other inclusion, Q inside R, right? Sending any P by Q to P by Q. Okay. Then again you can think about this inclusion from R into C, sending any X to X plus, I mean, I into 0. I mean, this I is root over minus 1, so X to X is enough. Okay. Example 4. Have you seen that group Z mod NZ? Have you seen that group Z mod NZ?
Yes, sir.
If there is anyone who is not familiar with the group structure, please let me know. Then I will elaborate it. Anyone? See, if you don't reply, I will have to assume that you are aware of this. Okay. So we can write this map Z to Zm, Z mod Mz. Sometimes they write it by Zm. Okay. But write this notation instead. This sometimes this can mean something else. So what do? They take A here, sorry, and they send it to the class of A, right? Is it a group homomorphism? Is it a group homomorphism?
Yes.
Check that this is a group homomorphism. Check that pi is a group homomorphism. This map. What about this map? if this is pi m, what about say psi m? This is just multiplication by m. So you are taking a to a to m times. Is it a group homomorphism? Check that this is a group homomorphism. Okay. Check that. Check that psi m is a group homomorphism. One thing, I mean, there are a few terms. I mean, if a group homomorphism F is injective, okay, if F is injective, then we say F to be monomorphism. Mono means one, okay, so 1 to 1. If F is surjective, we say what? Epimorphism, okay. If F is both, can you tell me what do we tell it? Isomorphism. Okay. Next we discuss one thing. So remark. Psi if G to G prime is an isomorphism. That is F is that, oh, maybe I should write this, that is a bijective group homomorphism. So F inverse from G prime to G is defined, right? Right? Defined by F inverse of Y is equal to X, where Fx is equal to Y, right? That is the natural definition.
Yes.
Show that F inverse is a group homomorphism. Can you show it? Can you show it? Because you see, we haven't defined isomorphism that way. We haven't defined that if F is called an isomorphism, if F and F inverse are both group homomorphisms. We haven't defined it that way. All we have said is that F is bijective and a group homomorphism, then F is an isomorphism. So the natural question should be, F inverse is a set theoretic map, right? But is it a group homomorphism?
হওয়া তো উচিত।
হওয়া তো উচিত আবার কি? Try it yourself. Are you trying at all? So
Yes.
let y prime belongs to G prime and x prime belongs to G be such that fx equals to y and f of x prime equals to y prime. Then f inverse of y prime, it should be what? Okay. Then if x prime, it is nothing but fx into fx prime, right? Because f is a group homomorphism, that is y into y prime. Clear? This implies f inverse y prime is x prime. That is f inverse y into f inverse x. Okay. So it is a group homomorphism. Okay. Next, what should we do? Okay, I think you can observe one thing, that if composition F inverse is what? So if G from G prime is F from F inverse, so F composition F inverse is what? The identity morphism of G prime, right? And F inverse compose F is what? The identity group homomorphism from G to G, right?
Yes.
Next. So first let f g to g prime. Whenever we write f g to g prime, you should assume that it is a group homomorphism. Okay, unless I mention otherwise. So kernel f, what is that? Set of all g belongs to capital G such that f of g is e g prime. Is this a subgroup? So let g1 g2 belongs to car f, then f of g1 is equal to e g prime equals to f of g2, right? This implies f of g2 inverse, whole inverse, is equal to eg prime, right? So what will be f of g1 g2 inverse? That is f of g1 into f of g2 whole inverse, right? That is what? eg prime into eg prime, that is eg prime, right? There we have g1 g2 inverse belongs to car f. I think you guys know that, right? So this is enough to show that this is a subgroup, right? There are two criteria. You have to show that if A belongs to H, then A inverse belongs to H, and if A and B belongs to H, then AB belongs to H. Like you have to show that the inverse is there and the multiplication is closed under multiplication. But together we can write it like if AB inverse belongs to G, then we can say that it is there. If for all A, B belongs to H, if we can show that AB inverse is in H, then H is indeed a subgroup. Okay. Hello. Is that clear?
Yes.
Yes, sir.
Shoroshmi, you are extremely quiet. And the others, Audrik is also very quiet, I think. So, those who are not participating enough, I'd request you guys to be a little bit more, what should I say? Be a bit more vocal. Okay, so I think there was a few confusion. There was a confusion regarding, the timing of this class. Okay, so at least for this month, the group theory class will be on Wednesday, 10:30 p.m. Okay, that is the schedule for the time being. But I think some of you have a little bit of a problem with the timing being this late. I think Shojato and Tamanna was telling me that if I can conclude it by 9 p.m. it will be extremely helpful to them. But on the other hand, Shoroshmi and there are some others, like Audrik and Spondon, they are not available till 8 to 9 p.m. Shoroshmi was saying that she is available, but she is available only on Tuesday, right, Shoroshmi?
Yeah.
Okay, so let me see. I think I am trying to manage, but don't worry. Whatever we will come up with, it will be suitable to all of you. Don't worry. So don't panic. Okay. So this is kernel. Okay, and you see that indeed this kernel is a subgroup of G. But what about, I mean, whenever we are talking about kernel, the very next thing we will be looking to define is image of it, okay? Or sometimes written as FG. So what is that? FG is the set of this form, okay? I mean, just the image, But is this a subgroup of G prime? So let G prime 1, G2 prime belongs to f of G. So there exists G1, G2 belongs to G such that f of G1, f of Gi equals to Gi prime, I running from 1, 2. Okay. So now you see what is f of G2 prime inverse, what is f of G2 inverse? That is f of G2 whole inverse, that is G2 prime inverse, right? Since this is of the form f of G2, f of something, right? So G2 prime inverse is of the form f of something. This thing is inside f of G, right? Also f of G1, G2 is nothing but f of G1 plus into f of G2, that is G1 prime times G2 prime. So this is inside what? F of G again, right? Because this is of the form f of something. So this is also a subgroup of G prime, okay? Should I define what a co-kernel is? No, then before that I will have to define a quotient group. Just a minute, give me a minute, let me see how Hungerford goes about things. Subgroups, because I'm not following what I was supposed to do. I'm following Hungerford for the time being, okay? Because I think in that case it will be easier for you if I have a particular text. Okay, so let's talk about a particular type of subgroups, okay? Cyclic groups. So let G be a group and A belongs to G. Okay. Then this is what? I mean, what do I denote by this? We denote by this the elements of this form. Okay. So a square, a minus 1, everything is there. Okay. So you see that if you take any two elements from there, I mean a to the power I into a to the power j, I mean suppose you take this from this thing, a to the power I and a to the power j. So you can clearly see that a to the power I into a to the power minus j, what is that? That is a to the power I minus j. This is also inside this, right? So this thing is a subgroup, indeed a subgroup of G, right? This is said to be the subgroup generated by A in G if there exists an A such that this is equal to a G, then we say that G is cyclic and A is a generator of G. Is that okay? Look at the definition and tell me if you have any problems.
It's okay.
Okay.
Yes, sir.
Now you see this. If there exists an integer n belongs to natural number such that a to the power n is identity. I am not writing identity G because we are only talking about G here. Then if there exists an integer, then the least such integer is said to be order of G. That is, and is denoted by order of A. Okay. That is, if order of A is equal to m, then a to the power m is identity and a to the power n is not identity for any n with 0 less than equals to, of course a to the power 0 is of course n, but okay, clear? So m is the least power to which once a is raised, it will produce identity. Okay, a to the power m is identity, and a to the power n is identity for no less n. No less n. Okay. Remark, or maybe I should write observation. You know what? This thing, the order of a subgroup, that is the cardinality. Maybe I should write if G is finite, can you show that? What do you think? Okay, let's see then. So first write down this thing. Okay, what is this? A square and something like this, right? The negative powers will also be, I mean, something like this. I mean, can you observe one thing? Can you observe one thing that, so suppose suppose order of A is m, okay? Can you see what is A inverse? You see A inverse is identity into A inverse, that is A to the power m into A inverse, that is A to the power m minus 1, okay? So what I am trying to say is that it is enough to consider only positive powers of A in this group once G is finite. Once G is finite, okay, G is finite, this implies this is also finite, right? If G is finite, then of course its subsets are also finite. So if the cyclic group generated by A is finite, it is enough to consider only the positive powers. Clear? Clear?
Yes, sir.
Maybe I should write with E. I mean A to the as it okay. So say there is A to the power K, okay, right? Or maybe I should write. So how many elements are there? K plus 1, right? So we need to show that K plus 1 is M, right? That is our target, right? Okay, let's see. So you see, I'm trying out an easier way to show it. Just a moment. in Hungerford they have defined it directly, that order of A is the cardinality of this thing. That is in a way obvious, but okay, let's see. So case 1 is what? K is less than M. Okay, no, maybe not like this. So if K is greater than M, then what you have is that a to the power K is equal to a to the power M into a to the power K minus M, right? That is a to the power K minus M only, right? Right? Okay, no, maybe let's write it this way. If K is greater than M, let's do this. See, K is an integer, right? So we have this. So QR belongs to Z, right? Maybe belongs to natural number. We can do this, right? Division algorithm, where R is what? R is this. Clear? So you see, once you do a to the power K, you get a to the power MQ into a to the power R. You see, this thing is identity, right? So you get a to the power R. Clearly? So a to the power K is a to the power R. Okay? So you see, if you come back here, you can replace e to the power K by a to the power R, right? Right? So mod A becomes what? You have a to the power 0, a to the power 1 and 2, a to the power m minus 1. Clear? Because whenever you have something greater than equals to m, you can just divide it by m and take the remainder. Clear? So that's how you get that. You don't need it. That is direct. That order of, this group is basically nothing but m, which is order of a. Clear?
আচ্ছা এই জায়গাটাতে মানে এ টু দি পাওয়ার 0 থেকে এ টু দি পাওয়ার m মাইনাস 1 কেন হলো?
So whenever you are taking something like a to the power m, it is again identity, because of the definition of the order. If you take a to the power m plus 1, you get a to the power m into a. That is, you are getting a. You look at this. Whenever you take k, okay. Then a to the power k is what? Is equal to a to the power r, where r is the remainder when k is divided by n. Then r is all. Then by definition r is always less than m, right? So only those powers of m will survive in the group which are less than m.
Yeah. Got it.
Do you know what a direct sum is? Okay, so we see we are about to stop here, but before we stop, the exercise is the homework. Okay, the exercise is the homework, but first of all, see, there are some examples you don't need to write, need to try. Don't try this, okay? So don't try. Of course you will try, but once I take the next class, then you will try it. So you will try. Don't try. Whenever you see Sn, don't try it. Okay. Sn is the symmetric group generated by n elements. Don't try it. Like 8 you don't try. 14 you don't try. I mean, whenever you see something like this, SN type of things, don't try it. Clear? We will define what SN is in the next class.
What is the homework? The exercises.
Exercise, I mean the second exercise, I mean page number 32 in my book. I mean exercise 2 maybe? Yes, exercise. That is the homework. If you are not willing to do the homework, please don't attend the course. It is as simple as that. Because see, this is not an MMath course or a JAM course where I am bound to see all the assignments. I am just bound to do them. If you don't do it, then don't attend the course. It's as simple as that. This is not a 1 year course where we are just we have just readied a material and we will just go through it. If you are not willing to do it, you don't need to do it. Just don't need to do the course. Just one thing I need to tell you, that you remember in the last class we have proved Lagrange's theorem, right? So what was Lagrange's theorem?
Order of subgroup divides the order of the group.
That if H is a subgroup of G, then order of H is the order of G, right? That was the group. I mean, of course, G is finite.
G is to be finite.
So you see, if A belongs to G and H is this thing, though you have order of A is what? Order of this thing, and this is supposed to divide the order of group G, right? So you have, that is the statement. So order of any element of G divides the order of G. Okay, this is our way of proving it, but they will probably prove it in a different way. There is no harm in proving a statement in two different ways. So this is one thing I wanted to tell you. Is there anything else regarding order? Just a minute, let me try.
Sir, any element of the element generated the group.
No. Do you need A to generate the group? You look at it. I don't need. I have only taken an element of G. Okay, think about it. Do you guys know what a dihedral group is? Okay,
I don't know.
let me tell you what a dihedral group is. Okay.
স্কোয়ারের পজিশন গুলো চেঞ্জ করে এরকম কিছু আছে।
I don't. Okay, then let's do one thing actually. Just a minute. জায়গাটা okay, you know what an infinite cyclic group is? So you see clearly, I mean, in our notation, I mean, in our definition, while we are defining a cyclic group, you see the finiteness of G was never assumed, okay? the finiteness of G was never assumed. So you don't need G to be finite, okay? Like example, you see Z is an infinite cyclic group. Okay, so you see Z is generated by 1 and also Z is generated by -1, okay? Okay, so you do the exercise. So in the next class, we will, in the next class I won't show the exercise, I mean see the exercise. So next class is on cyclic groups, okay? So in the next class we will be doing cyclic groups. Cyclic groups, yeah, that is section 3 and SN. So once I will do cyclic group, then I will do SN, okay? No, not SN, D2N, then SN. Hey, Tamanna, remind me in the next class about this, okay? That in this order we will go. First cyclic groups we will do from section 3. This is a very small section. We will first, we will first do it, and then we will talk about D2N and then SN if possible. Let's see. Okay.
Sir,
Yeah.
sir, one generate negative integer also.
Yeah. Why not?
Sir,
Can
how?
can be generated by negative integers.
Sir, मतलब generate मतलब 1 plus 1 plus 1 we generate that way ना 1 plus 1 2 1
Very
plus
good
1 plus 1
question.
3.
Very good question. But have you noticed it? This n was from Z. Have you noticed it? Not from natural numbers.
Yes. Okay.
So you want to tell me, you want to show me. So suppose 10. I mean, how do I do this, right? So you see, you can multiply -1. I mean, I'm talking about. So I mean, one thing it is clear, right? I mean, when we say A star A, this is basically A plus A in Z, right? 2A, right?
Yeah.
Because in the group, so you can do this like this, okay? So if you can just write for any n, it will be -1 times n. I mean, that is the generator, you understand that by definition, okay? N is in Z, so you don't need to worry. If n was taken from natural number, then what you are saying might have caused some problems, okay? Clear?
Okay. Yes, sir.
Okay. So, Tata.